Welcome to a lesson with Dr. Powell. Let's look at an example of using a fiber box diagram to illustrate how there is an induced map that goes from here to here, where this is a domain, this is a codomain, this is another codomain. Now, what in the world do these mean? This means the skip pattern merge, where we skip every 12 to be in the same box. So that means that 0 is in the same box as anything that's 12 away from it. So 12, 24, or multiple of 12 away, and backwards -12 and so forth. So that's one box. Similarly, 1 is in the same box as 13 and so forth. There ends up being 12 different boxes, and all of the integers are split into 12 boxes. So really, what does this mean? It means the 12 boxes. So the things are boxes, the 12 different things. So you can represent them as numbers 0 through 12 if you wanted to, or 11, I guess, because 0 is the same as 12. So 0 through 11, or you can do 1 through 12. In fact, I've kind of done that right here. We can think of our domain right here as being represented as numbers 1 through 12 if we wanted to. Those are representatives of each box here in this partition. And the skip pattern merge thing, okay, of the different chunks of the integers. All right, and similarly, this could be thought of the same way. There's 6 boxes here, there's 6 things here. Here there's 3 things. So there's 12 things here, there's 6 things here, and there's 3 things here. It's a set of 3 things, a set of 6 things, and a set of 12 things. Now, what is this function and what is this function? Okay, so this function right here that goes from these guys 1, 2, 3, all of these right here, these 12 different things, it comes to this one. It means basically to put. So let's see, if we have a 1 right here, where is it going to go here? And it's going to go to the box in here that's the same that that has a 1. So that's how we're going to define this and see if that works. So let's see, 1 is going to go to the box in here. So let's suppose this has this has 6 things, so 1 through 6. So let's list that out here. Okay. So let's see, 1, 2, 3, 4, 5, 6. Okay, so 1, okay, is going to go to 1. Okay, 2 is going to go to 2, 3, 4, great. But when we get to 7, where's that going to go? Well, 7, which box is 7? And 7 in this guy, well, 7 is 6 away from 1, so it goes back to 1. And 8 will go to 2, 9 will go to 3. So basically we have a nice function here. So that's what this function is right here. We've divided, let's see how this function has partitioned this domain. So it's partitioned it because 1 and 7 are being sent to the exact same location. Right? So 1 and 7 are being sent to the same location because they're 6 away. 2 and 8 are being sent to the same location. Let's see, 3 and 9, because they're 6 apart. Those are 6 apart, 6 apart, 6 apart. So what I've just done, so this top function, I'll call it f, I have just partitioned this original domain right here into chunks, given what this will do. So it'll take things in here, and if they're 6 apart, they go to the same place. So it's a way of, and I've successfully chunked this up very nicely. Okay. So now this is a well-defined function if you just if all you do is just label the elements of here as 12 different things, and then you just grouped them like this. Now, why is it a well-defined function? Because we just made a partition, and anytime we make a partition, that's a function. So if you just think about strictly things here and things here, we haven't talked about any kind of structure preservation or anything like that, but just as is, we do have a function, and that's all we're looking at the moment. So we're not thinking about these functions or maps as being reserving any kind of structure. They're just set maps right now at the moment. All right, now what about from here to here? Let's think of it similarly. Um, let's let things go to the same place if they're 3 apart. Okay. All right. Okay, so um, well, let's see. 1 will go to the same place as 4, which actually goes to the same place as 7, which goes to the same place as 10. Oh my goodness. So it means all of these um, are 3 apart. So let's just suppose, let's let that be the partition there. Okay. And what about this one? Let's suppose all of, okay, 5 is 3 apart from that. 2 is 3 apart from 5. So let's let all of these go to the same place. So let's let this bottom function g just be defined by this partitioning. Okay. Now, if we've defined, now of course, we made these partitions. We could just define functions by taking these partitions, right? Now, do these partitions actually yield a well-defined function that goes from here to here? Well, it does, because the partition for f, notice that it is completely, it's a further partition. It just further chunks up the chunks that were for g. It further does them up. So therefore, we do have a function. What is it? Let's think about this. Let's label this guy as 1, 2, 3, 4, 5, 6. We can make a function table for this guy and see what it does. Okay. So the function table for h that we would have, input x, output h of x. Let's see, we're going to have a 1, 2, 3, 4, 5, 6. All right, so where does 1 head? Well, 1 will end up going to this chunk. Now we could label this chunk in here as simply being a 1. Okay. Where does 2 go? 2 is right here. 2 goes to this chunk, which is a 2. Similarly, 3 would just go to the chunk 3. Now, where does 4 go? 4 is right here. 4 actually goes to this chunk right here, this big chunk, which represents an element of this, which we could label as a 1. So that would be a 1. Similarly, 5 will go to 2, and 6 will go to 3. Now, this function, as we've written it, actually completes this diagram off, and you can see that it actually would make this diagram commute complete. Thanks for watching.